Methods like depth-limited search and iterative deepening are particularly useful if we have some knowledge about the problem. Maybe we don't have to go full depth after all. So for example, in the case of the map, if we know that any city can be reached from another city within some limit, at most L steps, where L is less than 36 in the example, so maybe we don't need to go through as deep in the search tree and just limit it to some limit L. Iterative deepening is an extension of depth-limited search that actually combines the benefits of BFS and DFS. So the idea is to iteratively increase the search limit until the depth of the shallowest solution D is reached. So which means that we're going to apply DLS with increasing limits. So DLS, remember, it's a depth-first search until some limit. So in the case of iterative deepening, we're going to do a first tree until L, and then we're going to extend L, and then we're going to extend L again until we either find a solution, right? We stop if a solution is found, or if the algorithm DLS within the limit L returns a failure that there is no solution until the limit L. Because most of the nodes are at the bottom of the search tree, it's actually not a big waste to redo the whole thing until we either find a solution or we don't find it. So empirically, we see that basically it's not a big waste of resources to do that. So let's take an example with the depth limit between 0 and 3. So for limit 0, we are simply exploring the root node. So it's going to be simple. Limit 0 is just staying at the root. For limit 1, we're going to do a DFS until limit 1. So we're going to start with the node A. We explore first, so we put B and C in the fringe. We explore B first and then C. And then after that, every node in the tree is explored. For limit 2, we're going to go deeper until the limit 2. So we're going to start over. From node A, we are going to add B and C to the fringe. Then we are doing a DFS. We're going to explore B. From B, we're going to extend to get its children. So that's D and E. So we're going to have now in the fringe D, E, and C. Then we're going to explore D, then E. So this subtree is explored. We turn to C. So remember, it's again a DFS. So that's C. We're going to explore all the elements of C, which are F and G, that these two are going in the fringe. So we explore first F and then first G. And after that, we have explored all, by depth first search, all the tree until the limit 2. So for limit equal 3, we're going to start the process over again. So I start with the root node A. We put the children in the fringe. Then we go deep into the hierarchy. So I'm going to explore, I will just do it here. So I'm going to explore this first path, and this second path, and this third path, etc. Okay, so I'm going to do that. And this is actually a DFS up till limit equal 3. But we started actually over, so we're going to do the whole tree again. That was for iterative deepening. You will get to play with this method in your programming assignment. You might have noticed that the arcs on the search graph may have some weights or costs. For example, it may be the distance between two cities. And so far, the search algorithms we have been using do not leverage this information. So how can we leverage this information to help the search to find the optimal solution? So remember, BFS will find the shallowest solution, which is the shortest path, which can be costly. What we want is the cheapest solution, not the shallowest solution. So the idea then is to modify BFS to prioritize by cost rather than by prioritizing by depth, which means we are going to expand the node n with the lowest path costs, which we call G of n, rather than expanding it by the depth of the node. The approach is then to explore by increasing cost rather than by increasing depth, such as done by BFS. This method is called uniform cost search. The uniform cost search algorithm is very similar to BFS in the sense that we're going to explore layer by layer, but in this case, we're going to use layers for uniform cost search will be determined by the cost G of n. So remember, G of n is the cost to go from let's say, the root of the search until the node n. So this is going to be the cost G of n. So this is how much we need to spend in terms of driving or other kinds of costs to reach n. So the search will now be driven by this function f of n, which is only G of n. So we use f of n to stay general, and the main reason is that the function f of n, later on we'll see it for a star, is slightly different. There will be some other parameters that we take into consideration. All right, so remember BFS uses a queue, which is simply a list in which we put the elements and we pick them first in, first out. In the case of UCS, we use a heap, which is a priority queue, which means that we're going to pick them out of, to pick the elements or the nodes from the fringe by prioritizing according to the function g of n. So in this case, it's the main difference between UCS and BFS. All right, so we're going to create this heap, and this heap will include all the elements in the fringe or the frontier. And whenever we need to pick an element, we pick the element with the minimum cost. The other difference is that we're going to also make sure to handle, whenever we add the elements in the frontier, we do the same thing as for BFS, but then if the neighbor is already in the frontier and we found the shortest path, then we are going to decrease the key. In other words, if you suppose we have a node to which we are going to reach it in some cost, let's call it C, and this cost is actually going with this node in the fringe. And if we found the shortest path, let's say this one, then we're going to make sure to decrease the cost because we found the shortest path to end than the previous cost. So other than that, the algorithm is very similar. Again, we are going to search by cost, not by depth. So there will be layers. We are going to explore the search tree layer by layer, but these layers will be somehow jagged because they will be driven by the cost, by an increasing cost in the search. To fix the IDS, suppose we want to go from the city of Chicago to the city of Sault Ste. Marie, right? So if we do a BFS, we're going to find this two-step solution, which goes from Chicago to Duluth, from Duluth to Sault Ste. Marie. And the cost of this solution is 157 plus 110, right? So it's going to be, we need to spend 267 kilometers to get from Chicago to Sault Ste. Marie. If we use a BFS modified by cost, which is a uniform cost search, we're going to rather pick this path here, which is Chicago, Pittsburgh, Toronto, and Sault Ste. Marie. This is a path of size 3, which will not be picked by BFS, but UCS will pick it because the distance or the cost for this path will be 81 plus 80 plus 90, which will make a solution of 251, which is cheaper than 267. So UCS will pick this second path here rather than the other path.